Hi, IB Physics kids. Mr. Tima here. Going to go through parts of our notes. We're starting a new chapter, one-dimensional motion, or chapter 2 in our book, which is called mechanics. Okay, and when you think of mechanics, I always think of something that's mechanical. Okay, that's moving. Okay, like moving parts, gears, things like that. So when we look at this right now, how do we know that train's moving? See that train down there? How do we know it's moving? So if we look at it, some of you are going to say, well, we know it's moving because of that smoke. Okay. And we can tend to think that that train is moving to the right because the smoke's coming to the left. So, how do we know something has moved? Well, it's actually very simple. You have to look at what's around it or a reference point. For example, if you close your eyes, if you look at something that's in front of you, you close your eyes and you open your eyes, and it didn't move relative to anything around it, then you really can't tell if it moved. Even if somebody would have came in when your eyes were closed, picked it up, and put it back down exactly where it was, you wouldn't know if it moved. It's the same idea that if someone paid you to move a desk across the room, and let's say you do that, you leave and someone else moved it back, and when the person came in to pay you, they go, well, the desk didn't move, even though you moved it. There's really no proof unless we look at what's around it or compare it to a reference point. So we look at a reference point. That's the starting point of the coordinate system, also known as the origin, and it can change its system only. You cannot change what it is once it's established. So, like for down here with the kid kicking the ball, which it's not going to end well for him, but basically we're saying that kid's kicking the ball forward. When the ball comes back to him, we can't all of a sudden say to the right is forward. To the left was forward in this picture, so to the right has to be backwards. You can't change it in the middle of something. This reference point can be kind of confusing if you look at things at different angles. So, for example, if I'm watching the plane at the bottom, this is the same plane. But if I watch the plane fly across the screen from left to right, I'm going to say that the bomb or the ball or whatever it's dropping is also moving to the right. Okay, it's also moving to the right. But if I put like a camera above it, let's say I'm flying in an imaginary plane above this plane and I'm shooting down, it doesn't look like the ball's moving forward. It looks like the ball's dropping straight down. Okay. That same thing can happen in a car. So, for example, if I'm in a car and you go driving by, I think you're going by me at 70 miles an hour. But in the car, you might be asleep. It's not like you're moving at 70 miles per hour. You don't feel yourself moving at 70 miles per hour. Distance versus displacement. Again, a lot of the stuff that we're talking about, you should have learned in physical science. But our distance would be this long, curvy path, the total. Distance can never go down, it can only go up. All right. The displacement is exactly how far you are away from your starting point. I don't know. I love this cartoon. Okay. He says, okay, here's the play. Run 1 yard, turn around, I'll pass it. He says, one lousy yard. How am I supposed to show you my sweet juke moves in 1 yard? I don't think I can throw farther than a yard. He's like, wimp. He's like, all right, run 24,880 miles and 1 yard, turn around, I'll pass it to you. He's like, all right, now we're talking. Well, that 24,880 miles is the circumference of the earth. Okay. So he's literally telling him, why don't you run all the way around the earth and 1 yard? So his displacement is only 1 yard away from him. Okay. So it's a stupid little science joke. The guy that does these was a science teacher. But it's like instead of he's going to run a huge distance, 24,880 miles and 1 yard is his distance. His displacement is still only 1 yard. There you go. Displacement is a change in position, not in direction, in a certain direction, not the total distance traveled. You guys should be familiar with these formulas. All right. Velocity is a change in displacement, while speed is a change in distance. So your speed can change. Okay. Your velocity can also change, but they're not always the same thing. Here's a great example, what I like to call the bet. I used to always call this the bet when I was doing stuff. Let's just say that this is our start line right here. and I go all the way around the track and I'm racing and everything like that, and I get all the way back, okay, to the start finish line, okay? What happens is let's just say I go all the way around this and my distance is 100 meters. Okay, it's 100 meters all the way around here. And let's say it took me 10 seconds to do that. Well, my speed is 100 divided by 10. So my speed is 10 meters per second. Okay, it's 10 meters per second would be my average speed all the way around this. What would be my average velocity though? Velocity is displacement, right? So even though after 10 seconds, I end up right back where I'm starting from. So I go all the way back around again, and in 10 seconds, I come right back to where I started. Technically, my velocity there, because my displacement is zero, that'd be 0 divided by 10. My velocity is 0 because really I have not changed my displacement. Okay? So though my speed is 10 meters per second here, my velocity is 0 at this point. All right. There's a difference between average velocity and instantaneous velocity. Average velocity is kind of how we talk in the Midwest. It'd be like, I went up to grandma's house up in Toledo. Well, how fast did you go getting there? People say, I went about 70 miles an hour the entire time. Well, you didn't go 70 miles an hour the entire time. Okay. You backed out at 20 miles per hour. Then you gunned it on the highway, but you went about 70 miles per hour. You take your total displacement and distance divided by your total time. While instantaneous velocity is at that exact point in time. Like when the state troopers are pulling you over, they don't care about, well, hey, back when I was in the city limits, I was only going like 24 and a 25. So if you average that in, they don't care about that. They want to know your velocity at that exact point in time. So again, if I leave my house, which is basically Westerville High School, I'm just north of Westerville South High School. If I go, I might only get up to like 25 miles an hour, maybe 35 miles an hour. Then I'm going about 65, 70 miles an hour until I get here. And then you all know there's a little bit of traffic on Sawmill, so I got to slow it down. And then if I get to Scioto, maybe I'm going 40 on hard road. Okay, my average might only be 45 miles per hour or 55 miles per hour for the entire trip. But my instantaneous would be different at every single point. Okay. Motion dot diagrams. This is pretty easy. I like to think of these as like the Hansel and Gretel, okay, where they were kids. Remember, they get lost in the wood and they drop breadcrumbs. Or you can think about if I had a bucket of paint and every second it would drop a little drop of paint. Okay. So for example, if I'm just sitting here, this guy's not moving, just sitting there. The dot's just sitting there. Okay. If this guy takes off and he has a constant velocity, each dot will be equally spaced. Okay. Each dot will be equally spaced. So let's say a runner starts at rest and then is speeding up. Well, the reason we know that they're speeding up is because the distance between each dot is getting larger. This one is slowing down because the dots are getting much closer together. This one is both speeding up and then that person is slowing down. Okay, let's take a guess at what's happening here. I want you to take a guess. I want you to think, what is happening here? Could you describe this motion? Hopefully, you're saying they move at a low constant velocity and then maybe they take off. Or if it was a story, this person was walking and then something jumped out of a bush and they take off running. How about this one? Try this one. All right, hopefully, you're saying, hey, they were moving faster than before. So maybe you're out for a jog and then something jumps out of a bush and then we take off faster. A lot of things jumping out of bushes here. Number 3. All right. What if you were like sprinting and then all of a sudden you realize that thing's not chasing you anymore? And then we slow down to like a slower jog. Again, faster than up here, not as fast as here, but still like maybe like a quick walk or a slight light jog. And then finally, this one, give this one a shot. sprinting, slowing down, and then sprinting again. So maybe something was chasing you, you start slowing down, then you realize, that thing's right behind you again, and you take off sprinting again. Again, if you think of this as the dot diagram, if I measured you at each one of these little stopwatch guys, if you're moving at a constant velocity, if we're 10 meters away, let's say it takes you 1 second to get to each one of these guys, then we'd say that our velocity, our average velocity would be 10 meters per second. 10 meters per second. Again, we got to be able to graph that. You have time intervals, things like that. This should all have been done in physical science. Notice the error bars down here. Love that. Notice the error bars. Okay, so relative motion. This is what Einstein was talking about. This is the basics of Einstein's theory of relativity. Now, I do love that we're an IB, so I love the names, okay? Carmen and Miguel, okay? But just think about this. You've all experienced this in a car. When the train goes by to the right, Carmen's going to say, hey, Miguel is traveling at some speed to the right. Let's say it's 40 miles per hour. She also would say, hey, passenger A and B are also traveling at 40 miles per hour. But on the train, Miguel and passenger A and B are going to say they're not moving because relative to them, they're not moving. Okay, but they're going to say that Carmen went whipping by the window. It's the same idea as if passenger A was asleep. Passenger A doesn't feel like they're moving 40 miles per hour. But to Carmen, it looks like she's moving 40 miles per hour. You've all done this in a car when you're sleeping. Quick. In your car driving 100 kilometers per hour, you see a red light a quarter mile away. So you slow down to a stop. Situation 2, a deer runs out in front of you. You slam on your brakes and come to a stop. Which situation do you feel physically more? You should be saying situation 2. Okay, you've all been on there with the mom brake, you know what I mean, where the arm shoots across, like it almost like chops you in half. Okay, the mom brake, obviously. Okay, now why does that happen? Well, because of this thing we call inertia, because we are not allowing ourselves time to slow down, we feel it more. We've all been on the school bus where they slam on the gas and slam on the brake, and your body keeps moving back and forth. And we'll get more into that when we get to Newton's laws. Acceleration. We're talking about a change in acceleration. All right. Acceleration, by definition, is a change in velocity. All right. All right. Some of the last things we're going to talk about here. If a baseball has zero velocity at some instance, is the acceleration of the ball necessarily zero at that instant? The answer is no. If we throw a ball straight up in the air, if that ball goes straight up in the air and it stops for just a split second at the top, technically it has zero velocity. But it still has acceleration because the earth is pulling that ball back downwards. So just because it has zero velocity doesn't mean it doesn't have any acceleration on it. If a passenger train is traveling on a straight track with a negative velocity and a positive acceleration, is it speeding up or slowing down? If a train is traveling on a straight track and has a negative velocity and a positive acceleration, is it speeding up or slowing down? The answer is speeding up, actually. If the train is moving in the negative velocity, which means it's moving backwards, right? It's moving to the left, shall we say. It doesn't have to be moving backwards. I should say that was wrong. It's just moving to the left or in the negative direction, whatever our coordinate system is. Okay. But it has positive acceleration. It means it's speeding up. It's changing its velocity, increasing its velocity. It doesn't matter if it's positive or negative. So on a right and left situation, it could be speeding up in the left direction or the negative direction. When you're out for a bike ride, you slow down on your bike as you approach a group of hikers on a trail. Explain how your acceleration can be positive even though your speed is decreasing. This one's a little harder to think about, and not having you in class, we'll probably have to talk about this. But the idea is if I'm slowing my bike down, what if I want my acceleration to be negative? I want my brakes to engage. I want to slow my positive velocity down. So to do that, I can have positive and negative acceleration or an increasing negative acceleration in order to slow my bike down. Okay, so negative doesn't always mean bad. It can also be a positive thing for us. All right, you'll see this in your book problems. These are our book problems for this section. And then also we have a worksheet that you'll have to download, answer the questions, and then send me back your work. But other than that, trying to keep these videos short. This is part one. There'll be 3 parts to these notes. Again, have a wonderful, wonderful day. And if you have questions, make sure that you're reaching out to me. All right, have a great day.